Good morning again. All right, what we're going to do today, we've already gone through the anatomy of the respiratory system, external areas to alveoli. We've looked at Boyle's law. The next thing we're going to look at is kind of how the gases move out of the lung into the blood, from the blood to the tissues, and back around. CO2, the same thing. So we're going to look at diffusion, which means we need to kind of have an idea of concentration gradient. Now, because gases are going to behave a little differently than other states of matter, there's another one of those gas laws I have to sort of talk about. First of all, just imagine, for the sake of argument, the room you are in right now, room air, is 21% oxygen. Everyone's probably doing fine as far as gas exchange, hopefully at the moment. Then let's say you take a field trip. I don't know, one of you wins the lottery and you take the whole class when this junk is over, and we go to the top of Mount Everest. So we fly up there, get out of the helicopter, walk around on the summit. What's going to happen to us? We're all going to die. If we go to the top of Mount Everest, we'll die. So my question is this. Atmospheric air, it's 21% oxygen at sea level in this room, in your room, about 78% nitrogen, just small amounts of everything else. What do you think the concentration is of oxygen at the top of Mount Everest? So, Keith, you said less. No, it's not less. I'm just making that up, Keith. It turns out the concentration of oxygen in the free atmosphere is basically 21% no matter where you are. So how come when we go to the top of Mount Everest, we die because of lack of oxygen? It's 21% oxygen here, it's 21% at the top of Mount Everest. Why do we die? Well, the reason for that is concentrations of gases are not, you can't treat them the same as you do, solids and liquids and solutions. For example, if I told you I had a 1 liter jar of a 5% sodium chloride solution, and then I had another 1 liter jar with 10% sodium chloride solution, and I asked you, which one has more sodium chloride? You say the 10%. Yes, the volume's the same, that's got more sodium. That's true. But I could have a jar with gas in it and say one's 10% oxygen, have another jar, say the other one's 5% oxygen. Which one has more oxygen? You don't know. Could be lower than 5%. Why? It's because, again, that volume business, the volume of a gas is not fixed. It'll change with pressure. So here's my stupid example. Let's say you're sitting here at sea level. Get enough room here. So here's the ocean down here. And here you are on the beach. There you are. And what you have is, you have your pet, 5-gallon jug. So you got almost like we have in lab, 5-gallon carboys or jugs. So I'll draw it a little bigger here. Let's say here's your jug. Now this container, it's open to the atmosphere. So, you got atmosphere, got air out here, which is 21%. O2, that's rounded, it's like 20.95. We use 21%. It's open, we're at sea level pressure, which is 760 millimeters of mercury. So the air in this jar, there's no air going in, no air going out, it's all equilibrium. What do we have in here? Well, it's 21% oxygen as well, right? And what I'm going to do is imagine these little dots. I'll just put 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's just say they represent the oxygen molecules. There's 10 of them in there. I'm at sea level. I have 5 liters in my jug. 21% of that gas is oxygen. Now what I'm going to do, I'm going to stick a little balloon on the top of this. So I just snap it over the end. It's now closed. It's a sealed system. But it still has 5 liters of gas in it, and it's 21% oxygen. Now what I'm going to do, I'm going to take my pet jug, and I'm going to carry it up a mountain. I'm not going to use Mount Everest. I'm going to use, I believe, Mount Whitney. I think that's how you spell Mount Whitney. That's roughly 15,000 feet. Why Mount Whitney? Because I know the pressure up there a little better. It's just mathematically easier for me. So I'm going to start here with my little jug with the 5 liters of gas in it with a balloon. At sea level, I'm 760 millimeters of mercury, right? As I climb up the mountain, what is the one thing that changes as you go up? In elevation. Remember, pressure is due to this column of atmosphere. The gravity is pulling it down, it's crushing your body. As you go up to 15,000 feet, there's a bunch of air below your feet. That's not squashing you anymore. It's not exerting any pressure. So of course, what happens when you go up in altitude? The pressure drops. There's less air coming down and squashing you. So at the top of Mount Whitney, the pressure, let's just say it's 380 millimeters of mercury, give or take 15,000 feet or so. That's roughly the pressure. What is going to happen to this 5-liter container of gas if I reduce the pressure to 1/2? Remember, if you don't, P1, V1, initial pressure 760, initial volume 5 liters, has to equal P2, V2, Boyle's law. The final pressure is 380. So if I start with 760 times 5 liters, what's V2 going to be here? The gas is going to expand. That's why I picked these numbers. The pressure is half of what it was at sea level. That means the gas will double in volume. And in fact, what will happen is this balloon you stuck on the side will expand. Now you have 5 liters here, 5 liters here. Now no air's gone in or out. It's just expanded to blow up the balloon. Now as the air expands, nitrogen and oxygen molecules are all kind of mixed randomly. These 10 oxygen molecules, are they still going to be in the jar? No. I can't erase them on my whiteboard, but basically half of them, because the gas is expanded, half of them, 1, 2, 3, 4, 5. Now I have 5 up here, 5 down here. That represents the oxygen molecules. This is still 21% oxygen. What's happened is just the amount of nothingness. The space between the molecules has increased, everything expanded. But if I count 100 gas molecules at random, about 21 of them are still oxygen, whether I'm in the balloon or the jar. Now, the reason I picked a 5-liter jar, that's about the size of your lungs. So this represents the air at the top of Mount Whitney when you inflate your lungs. It's still 21% oxygen. If you count 100 molecules, 21% of them are oxygen, but the amount of oxygen molecules is actually a half. So there's half the amount of oxygen available for gas exchange. That's why, as you go up in elevation, you will start to become oxygen starved at 29,000, 30,000 feet, at least without any acclimation. You will die. There's physically not enough oxygen molecules in your lungs to move into your blood. So, when we're looking at diffusion of oxygen, again, we know diffusion is dependent on concentration gradient. I think we said last semester, particles will move from an area of high concentration to an area of low concentration. You can't use volume percent, because these are both 21%, room air, top of Mount Everest, but there's not enough oxygen at the top of Mount Everest. So what do we use? We use something called partial pressure. Now this in your textbook will be referred to as Dalton's law of partial pressure. What he more or less said is, if you think about it, standing here at sea level, you've got all this atmosphere above you, and the gas molecules are literally smashing into you. That's what exerts the pressure. Of all that pressure, because of the gas molecules smashing into you, what percentage of it is due to oxygen molecules smashing into you? Well, it's 21% of our oxygen, so 21% of the pressure. So that's kind of the idea of Dalton's law of partial pressure. What I want you to be able to do is just calculate it. It's actually really easy. To calculate partial pressure, room air at sea level, you take the atmospheric pressure, which will set at sea level. Again, you should know sea level pressure, times the volume percent. Well, 21%, that's 21 hundredths. That's what percent means. So it'd be 760 times 0.21. That's 21%. Just do the multiplication. 0, 6, 7. Hope I can do this right in my head. 0, 12, 14, 15. Add them up. 0, 6, 9, 5, 1. 2 decimal points. All right, the number right here is 159.60. The units are still millimeters of mercury. This is what's referred to as the partial pressure of oxygen. So at sea level, the partial pressure of oxygen, it's usually written as P with a subscript O2. You could round it 159, 160. We've already rounded the concentration of oxygen anyway. But that's the partial pressure at sea level. The partial pressure of oxygen is about 159. Now, check it at the top of Mount Everest. Now, Mount Everest It's still the atmosphere, so it's 21% oxygen, but what is the atmospheric pressure or ambient pressure? I don't expect you to memorize it, but at the top of Mount Everest, the total pressure is something like 220 millimeters of mercury. So what is the partial pressure of oxygen at the top of Mount Everest? Do the multiplication. See if I can find a blank spot here. Get on my stool. Can we see up here this far? Yes. So we'll take 220, that's the atmospheric pressure at the top of Mount Everest. It's still 21%. 0, 2, 2, 2 times 0, 4, 4, 0, 2, 6, 4, 2 decimal places. So at the top of Mount Everest, the PO2 is about 46 millimeters of mercury. Compare this sea level to this top of Mount Everest. That's less than a third. That's why you die at the top of Mount Everest. Or if you don't die, you're probably getting permanent brain damage because that's pretty much beyond the range of what we can tolerate for any significant period of time. That is the partial pressure. That's why when people go to the top of Mount Everest, what's littering the sides of the mountain? All these compressed oxygen bottles. You know, in extreme cases, what if you breathe 100% oxygen at the top of Mount Everest? Well, 100% times 220, the partial pressure would be 220. You'd be fine. That's also why in pressurized, jets, they're flying about 30,000 feet, roughly about as high as Mount Everest. If they depressurize, normally those are pressurized to a couple of thousand feet, it's no big deal. But if they get a hole in them, air leaks out, the pressure drops to ambient, something like that, everyone on the plane would pass out and die, including the pilot. This would be bad. So what happens? Oxygen mass drop down. You breathe that, you're breathing a higher concentration of oxygen, not 21%. That's enough to keep you conscious. Particularly critical for the pilots, so they don't pass out and crash. That's how you calculate partial pressure. So what you need to do is you multiply for any gas. This is true for oxygen, we can do it for CO2, you can do it for nitrogen. Take the total pressure, the atmospheric pressure or ambient pressure, multiply it by the volume percent. For sea level, I expect you to know atmospheric pressure is 760 millimeters of mercury. The volume percent for oxygen is 21%, volume percent nitrogen 78%. That's all you need to know. Any other values I'll give you. Like if I asked you what's the partial pressure of oxygen at the top of Mount Everest, I'd tell you the pressure at the top of Mount Everest is 220 millimeters of mercury. You could go from there. But all you do, for any gas, take the volume percent, multiply it by the ambient pressure. That's going to give you the partial pressure. That's what we use to determine what the concentration gradient is. So gases will move from an area of high partial pressure to an area of lower partial pressure. That's the concentration units we use for gases, not volume percent. It doesn't mean as much. Be able to calculate partial pressure. Again, no 21% for oxygen, 78 for nitrogen, and atmospheric pressure is 760. Any other values I'll give you. So it's just a multiplication question. Be a piece of cake. Let's see, what else? So be able to calculate partial pressure. That is Dalton's law is the name they'll give this. There'll be a couple questions on the next exam on calculating partial pressures, but that's how we calculate the concentration gradients. And you can calculate partial pressure when the gas is in the gas phase. As we'll see, you also calculate partial pressure if the gas is dissolved in a liquid. It's still PO2. You can have a partial pressure of oxygen in the arteries, a partial pressure of oxygen in the veins, in the tissues, and so forth. So that's our quick partial pressure lecture. I'll post this up and take care.